Hello and welcome to another LeetCode problem. So today we're going to be doing the problem of the day for June 4th. It's going to be number of provinces. So it's a pretty straightforward problem. It says there's n cities, some of them are connected while some of them are not. If city A is connected with city B is connected with city C, then A is connected to C. So a province is a group of directly or indirectly connected cities and no other cities outside the group. You're given an n by n matrix is connected where it is connected ij equals I if the ith and j city are clearly connected, and disconnected ij equals 0 otherwise. Return the number of total provinces. Okay. And so this is a really straightforward question. You can do it a couple ways. So first of all, how do we figure out the number of provinces? And first of all, how do we connect these things? And how do we figure out the number of total provinces? So let's just go through this example. So we're actually going to draw this matrix. It's a little actually hard to visualize the way they have it drawn, but let's draw it and then it'll be a lot easier. Okay. And so these are indices, but these indices are one index. So let's just say this is index 1, 2, 3. 1, 2, 3. And we have points 1, 2, 3. And so if we take a look, so here it's 0.1 and 1. Right, so I don't think row and column matters too much. Well, actually we could figure it out, right? So 2 and 1, yeah, 2 and 1 or 1 and 2, it doesn't really matter, right? It's the same thing. So 1 and 3 or 3 and 1 and so on. So you can do it either way. Like for this point, if it's 2 and if the row is which or the column is which, doesn't matter. But anyway, so let's go through this. So here means 1 and 1 is connected. Well, obviously 1 is 1, so it's connected. Here, 1 and 2 are connected, so we draw a line. Here, 2 and 1 are connected, but they're already connected, so you don't need to draw that. And 2 and 2 are connected, obviously, because they're the same. 3 and 3 are connected. So once we go this graph, we get these connections. Now there's a couple ways we could do this. We could do this one of two ways, and I'm probably going to do it, let me think of like one way to do it. I think I actually have done this like a harder problem with this as a sub-problem for other problems, but that's okay. So one of two ways you can do it is actually you can just loop through all of these. So let's say you have this 1, 2, 3, right? You literally just have a loop that loops through n times. So you have a loop that loops through every single number, and you have a visited set. And once you make these connections, you just, so like let's say you start at 1, you can just do a depth first search from 1 to every single node that you can get to. Okay, and then so you'll have 1 and 2 in the visited set. And then at every single node you start that wasn't in the visited set, that's one province, right? So we'd start at 1, we'd say, okay, and let's just say we have this res. So we start at 1, that's one province. We add 1 to the visited set, we DFS through the 1, we get to 2. And then we try to start at 2, right? Because we're going to have a loop. So we're going to have a loop that's going to go from 1 to n. So we go to 1. This is one province. We put in 1 and 2. We start at 2, and we say, is 2 in our visited set? It is. So we don't add a province there. Then we go to 3. 3 was not in our visited set, so we make this res equal to 2. We add 3 to our visited set. And then we do a DFS in all the nodes connected to 3. So that's one way you could do it. The other way is you can do a union find. Okay, so you do a union find, and what a union find does, just talking about it really quickly, is a union find with will connect nodes. And so what, instead of doing these graph connections in the loop, what we'd have to do is we have to do it another way. So let me just go through that really quick. So let's just delete all these things and let's show you how the union find would work. So the union find would work like this. First, we would make our result equal to n, right? Because originally we have n provinces, okay? And then we would go through these edges. So let's say we'd go, obviously we don't care about the edges that connect a node to itself like this, because obviously they're connected, it doesn't add anything, but let's say we go to this edge. So if we go to this edge, then what we can do is we can actually call union find, and we can try to connect 1 and 2. And union find has a union, so we can connect 2 and 1. if it returns true, that means we were able to make this connection. If it returns false, that means they were already connected. And so think about what it means if you make a connection. So if you make a connection, first of all, in a union find data structure, it's basically like drawing a path. So if you try to make a union of two nodes that are already connected in some way, it will fail. And so you can simply just say, okay, let's try to do a union for every edge I have. Now, what happens when I make a union? Well, every time you make a union, your res is -1, right? Because when you make a union with two provinces, your number of provinces goes down by 1. And that makes a lot of sense, right? Like, let's say you have, some provinces here. Like, if you have this province and you make a union with this province, now how many provinces do we have? We have 3, and we had 4. And so that's one way. That's the other way to do it, is you can do union find. So let's say, so here, we would be able to make a union, but then we'd keep going, right? So 2, 1, we try to make a union of 2, 1 again. And we try to do that, but they are already connected in our union find data structure or in our object. So that's going to fail. So that's going to be false. So we don't need to do anything there. Then 2, 2 is the same node, and 3, 3 is the same node. And so our res here would be n-1, which would be 2. And for the other example, we wouldn't be able to connect anything. Well, we wouldn't even check anything because none of these on the graph, all these are just nodes connected to itself. So those are the two ways we can do it. For the union find, there is an Explorer card for union find, or you can just Google union find. I will paste the Explorer card union find in my description for this problem. But we're gonna actually, which one do we want to do? Let's just do a DFS. So remember, for the DFS, we have to go through this is connected. We have a visited set. Yeah, and we have to have a visited set for this, and for union find, we'd have to have a data structure of these arrays. So either way, the complexity is going to be the same, I think. Okay, so we have a visited set. Now we have to, remember, we're going to make our result. Yeah, let's make our result 0 in this case, right? And then for every node we can visit, then we'll add that into the result. So let's do that. Now remember, first we have to actually make these paths. So that's going to be, yeah, right. So just say, is this an n by n matrix? N by n? Okay, so let's just say rows equals when is connected. Okay, there we go. Now, actually, for these paths, so the other thing is, for these paths, if we do a DFS, we do have to have an array of all of the paths. And I think actually if it's like a complete connected component, maybe it'll take up more space, right? Because we can have something like this. So maybe we should do a union find instead. Because if we have something like this, like let's say we have some nodes, and they are completely connected, meaning there's an edge everywhere, there's going to be a lot of edges. I mean, actually, no, it won't be that bad. It'll be... No. It will be bad, right? Because we will have n-1 edges from every single node. So we would be storing... we'll be storing like an n by n type thing. Or, yeah, our complexity would be n squared here when we're storing. And we probably don't want that. So in that case, let's actually do the union find. Yeah. Okay, so I'm actually going to code up the union find from scratch. I did copy-paste it in some other problem, but I'll code it up from scratch. It's not too bad. So, okay, so def int, and union find takes a number of nodes, and so it has a couple things. It has a roots array, which is just it starts off with every node is indexed to itself, actually. So let's do that. So that's just going to be what, n for, or I for I, range n. So that's the roots, self.ranks. And here it's going to be the rank of every node. It means like how long the path is. So union find has parents, and they're going to be connected to some nodes, and so rank just means like how long the actual tree is connecting the nodes. So okay, and so self.ranks here is going to be start off as 1 because every node is its own parent. So that's that. Okay, so that's the init. Now we need the find. So the find is going to take this, and it's going to take some node. And then I believe it's like if self.roots node equals node. So if a node is its own root, we can just return. Otherwise, we do self.roots node equals self.find. And then so we like recurse down. So self.roots node, self.find, self.roots. I think it's something like this. So we basically just have to keep going until we get until something is its own parent when that's the root. I think it's something like that. So hopefully that's right. Let me just double check. So self.roots node equals self.find self.roots node. Yeah. Actually, we want to find on the parent. Yeah, no, I think that's fine. Okay, we'll double check if we made a mistake, but I think that looks good to me. And then we need to return that as well. So okay, now we need a union. So union pretty straightforward. We just connect two nodes. So union's gonna be self node 1 node 2. So we need a root 1 and a root 2. So 1 root 2 equals self.find. That's going to be node 1. Self.find node 2. And then pretty much what we need to do is we need to check if their parents are equal, and if their parents are equal, then they're the same component, so we can just return false. So if root 1 equals root 2, return false. Otherwise, we need to make this connection. So we need to figure out which rank is bigger, and we need to connect the shorter rank to the longer rank, because that'll save us for traversal. So like, let's say we have some nodes like this, and then we have some other node like this. We want to connect the shorter node, the shorter parent, to the longer parent, because our traversal here would be 3. We're always starting at the parent. And if we do it the other way, where if we connect this to this, now this would be the parent, and then this traversal would be 4. So to optimize traversal time, we'd want to connect the shorter parent to the longer parent. Okay, so if self.ranks root 1 is less than self.ranks root 2, we make so then that would be self.root root 1 equals root 2, elif self ranks. So now we just have the other way. Root 1 is greater than self.ranks root 2 self.root root 2 equals root 1. That's the other way. Else we can do either one. So we'll just say self.root root 1 equals root 2, and now we have to increase the rank of root 2, because if they're equal, that means the rank of root 2 needs to increase. So self dot. And this stuff is kind of boring, but yeah, I would encourage you, if you don't know union find, to just look it up in the explore card, because it's definitely it definitely deserves its own like discussion. Okay, and so this is self dot ranks root 2. So we can return true here because we made a successful union. Okay, hopefully that is okay. I think it is, but we'll see. Okay, so now what do we have to do? Remember, so for a union find, we have to go through this array, right? This array of connected, and we have to try to connect nodes. And so we're going to start with a res equals to n, and every time that we were able to connect nodes, we're going to subtract 1, right? And then so we're going to have a union find data structure as well. So we'll call that union find. And we are going to pass in length is connected here. That's how many nodes we have. Let's just have a variable for that. So nodes connected. Yeah, we have a variable for that. So this is going to be num nodes. Okay, so now that we passed that into union find, so now we need to iterate through this grid, right? And so that's going to be for row in range num nodes, for a column in range num nodes. If row does not equal column and is connected, yeah, so it's connected row column. So we need to check for one values, right? So that's going to be 1. Then we need to do this union find. So if UF row column, this is going to be UF dot union, right? We're going to use the union. Okay, so if UF union, that means we made a successful connection here. That means res minus equals 1. Just return. Hopefully my union find is correct. I'll double check if it's not. Okay. This is needs to be down here. Okay. Let's see. How many things did I screw up? Probably a lot. Actually, no, this is root. No, never mind. No, actually, this should be root. These should all be roots. It's annoying. Okay. Yeah, let's see what else. Okay. So I did write the union find correctly. That's pretty shocking. Cool. Okay. So let's think about the time and space complexity here. But yeah, I'll definitely link this union find. It's not super intuitive, and you're gonna want to, like, if you haven't done this before, I would recommend doing, I think I wrote in my main video to do explore cards for graph, and it's in the disjoint set data structure, but I'll definitely link that in the future, or I'll link that in the description of this video. Okay, so let's think of the time and space complexity here. So for time, so this is n squared, right? Because we have a nested loop. So that's already n squared. Now, let's think of the other things we do. So this union find stuff, the union and the find are supposed to be, I believe, in constant time, or as close to constant time as can be. So these operations right here will be constant time. They try to mimic constant time. It's not exactly constant time. So that's going to be n squared. Now for this space, so we do have to have an array of n for like these ranks and these roots. That's going to be length n. Let's see if we use anything else, right? So we have num nodes. We have a union find data structure that has these roots and ranks that are, like I said, space complexity of n. And then we just call, yes, I think this is space n. So yeah, if we did do a DFS and we had a dictionary, I believe we'd have n squared space, because like I said, if we store these paths, and we had some fully connected thing, right? Like even for this, or actually, yeah, so for like this picture right here, every node would have n-1 connection. So it'd be like n-1, which would be n squared for space here. So hopefully that makes sense why a union find is a more efficient. Now, obviously, average case, they'll be roughly similar, and DFS is easier to code, but I think union find is a little bit more efficient. Okay, so that's all for this problem, and if you like this video, please like and subscribe, and I'll see you in the next one.